Hello, this is Isabel Madavi, and today we are presenting our final optics lab project, which we did on optical tweezers. The topics covered in this presentation go over the various important physics concepts related to the use and setup of optical tweezers, as well as the actual steps we took in our lab, including the calibration and using of optical tweezers. Optical tweezers was first used by Arthur Ashkin in 1986, who first reported the detection of optical scattering on small particles in 1970. This concept was what ended up helping him discover and use optical tweezers later on. Optical tweezing is a method that can be used to trap microscopic objects inside a focused beam and has advanced to the point that researchers can manipulate objects on the scale of single molecules, which has been especially impactful in the field of biology, where the study of small particles is essential. The physics of optical tweezers. Optical tweezers work by overlapping a split and expanded Gaussian beam into the sample that we are studying in the tweezers, which is inhabited by small dielectric objects suspended in a fluid medium, on the size scale of microscopic or submicroscopic. When the photons in the laser diffract as they travel through the bead, their momentum vectors are changed. As the intense light in the center begins to diffract away from the center of the bead, the momentum of the system is conserved by a restoring force on the bead which pushes it towards the center of the beam. This process also occurs with the weaker rays at the outer edge of the beam. However, they are less intense and therefore cause a weaker restoring force. Brownian motion. Brownian motion is the highly random motion of particles when they are held inside of a fluid medium, either a liquid or a gas. The many small, highly chaotic molecules within the medium are constantly colliding with the larger particle, the bead in this instance, causing it to experience a seemingly random movement pattern through the medium when seen by an observer. This is important to optical tweezing as it allows us to easily analyze the viscosity of our sample, and thus the ease and speed at which we will be able to manipulate particles within the medium. The viscosity of the fluid is a measure of how thick the fluid is, and this is inversely proportional to the Brownian motion that we see for the particle suspended within it. For example, a particle in syrup would see very little in the way of Brownian motion when compared to a dust particle suspended in non-viscous air. In our case, we can measure the mean squared displacement on several particles over time and relate it to viscosity through this relation of m equals 2 times kb times t all over 3 pi n effective r, where n is our fluid's viscosity, r is the object's radius, t is temperature, and kb is the Boltzmann constant.
The holding force of an optical trap, since we know viscosity now, we also know that it's connected to friction resistance, simply because if a fluid is more difficult to move through, you would assume that the frictive force exerted on that particle would be greater. I mean, we can actually show this relation here, where this friction force is directly proportional to the viscosity, as well as the radius of the moving particle, as well as the velocity here. Since this is directly opposing the motion of our particle, we can actually use our optical tweezers to move the particle in space, and when it drops it, the velocity with which it drops it, we can calculate the force that equals the maximum holding force of our trap. So, if we're just barely holding on to it, and we can plug in Vmax here, we can equate this to be the maximum holding force of our optical trap. This can actually be a little frustrating to do, because being able to move a particle that quickly through a medium for enough time to get it up to full speed and everything when there's so many beads around can be hard, but it is manageable. The most difficult part of handling the optical tweezers is definitely the calibration here. So it's a very sensitive instrument because you have to have everything perfectly collimated and calibrated to make sure that our optical trap is properly aligned inside the sample plane, so that we can actually manipulate the objects. So firstly, we need to take this laser here, take it out of its mounting. There's a little collimation lens on the front. We're going to point it at a wall, and we'll twist this lens until there's a very fine point on that wall so that we know that it's well collimated. We'll put that back in. We need to take out this beam expander. And at this point, we place an alignment plate right here with a little bullseye that will be at the very dead center of this mirror. And we'll make sure that the laser is pointing dead center on that mirror. We're then going to adjust this bottom mirror so that it is pointing directly vertically into this top mirror, which we'll end up doing by just going ahead and unscrewing this mirror and seeing where the laser's coming out. We'll put that back in. And then we can take off a cap over here and again repeat this step, make sure it's coming out of the center. And then we know it's straight and calibrated. At this point, we're going to put our beam expander, which is these two lenses here, which is going to take our thin, small beam and expand it to around twice its radius. And at this point, we also need to repeat a similar collimation step where we need to adjust the distancing of these two lenses, which you can initiate at 12 centimeters, but it's a little slightly different than that, to ensure that the laser is collimated after it leaves the beam expander. At this point, we have an optical trap functioning and in our sample plane, which we can manipulate by moving the sample stage with the servo motors that are attached. And now we're able to see, and I'll actually show in a second, the functioning of the optical trap. So we're basically able to just move around and grab loose beads, which will snap into place in the center of our trap, and we can move them around. If you don't see the optical trap, or you can't trap anything, your setup is probably misaligned, which will make you need to realign it, and be very careful about your calibration steps. Now, we have a couple of videos here demonstrating this. In our first one here, we don't actually move the bead. We do have one trapped, but it's not moving. And this way you can see here Brownian motion. So you see these little wiggling beads. That is Brownian motion, little random movements. Here we can trap a particle. You can again see Brownian motion around. This is a trap particle here. You can see that sort of bright center, as you see here, and we can move it around. And in this way you can manipulate small particles. Now, we also have just 2 more example videos. So if you reduce the holding force, right? Because we know if you trap the you trap a bead in the optical tweezer, you know, you're going to see heavily different Brownian motion because the majority of the force being applied to the bead is now, you know, a restoring force. You're going to see a lot of limited movement here. But if you take that holding force low, you actually can still see inside the trap just a little bit of Brownian motion while you're still able to move the bead. And in this way, you can still move the bead as it's wiggling and manipulate it around inside this microscopic environment. Now, of course, you do need to be able to see, you know, you'll be able to track mean square displacement for viscosity, as we can see earlier in our presentation here. So we're able to take a motion tracking software such as Viana and do motion tracking where it takes our bead, tracks its motion, and then we can very easily get a demonstration of Brownian motion as well as vast amounts of data about its movement and calculate this mean square displacement for viscosity and maximum holding force. Thank you for your time. This has been Joey George and Isabel Madavi.